So with the optimized geometry of the H2 molecule, we try now to compute the total density. We need to adapt the input for that. First, we are going to work with the optimized structure, and we only need to perform then a self-consistent field calculation. So the calculation type changes to SCF. Then we still have the same amount of atoms in the unit cell, but we need to open the last output, find the final geometry, and change the values to those, and that was 0.77 angstrom and 1.52 by calculation. Then please note that you need to make sure that you know the prefix of your calculation, and you need to specify the output directory. These two things you need to note down, because we're going to need that in the post-processing. With the input for the self-consistent field calculation, now the self-consistent field calculation is completed. And if you inspect the working directory with list ls, you will see we have now a temp folder. That was the name of the output directory. We can change the directory into the temp folder and inspect it. And we see that we now have a directory and a file that is named with our prefix. In the directory, there are a couple of important files. There's a charge density file, there's a wave function file, and there's also stored the potential we use to compute the system. Okay, just so that you know that. We change back into the directory where we have our input files, and I already prepared the input for the post-processing. Here the important parts are that the output and the prefix are consistent with the input file for the self-consistent field calculation. The other important parts are that the plot num is 0, so that the electronic density is plotted. There are other options, and if you have time we were going to talk about that. But for now we want to plot the total charge density, and that is the total electronic charge density. Then to specify the file format and the information that are actually stored in the output file of the post-processing, we have the iflag3 that plots the 3D charge density. In principle, we could ask for a volume slice. That would be, for example, a 2D density, or the projection onto one axis when we want to consider, for example, charge transfer across the surface. Anyhow, so that is 3 because we want to look at the 3-dimensional output, and the file format of the output file. Output format is 6, that will give us a cube file. Cube files are pretty standard and can be read by many visualization software such as Vesta or VMD. I put the complete file into Google Drive, so you can take a look for that. But in principle, if you adapt now the prefix and the output directory, it should work for any system. You can then run the post-processing file with the command run_pp, and you provide as argument the prepared input that's called pp.in. So that calculation is done now too, and the last file that was created we can check by ls minus lhtr multiplication sign, and we see that just now there was the file created named charge density.q. And that is consistent with the file we ask it to write in the file output. Now the name, the charge density, is a cube file. It's written in the header of the file. It's a cube file created with PW as that consistent field calculation. The first 1, 2, 3, 4, 5, 6 lines are information in our system describing the grid density of the points on which the charge density is computed, plus the position of our hydrogen atoms in Bohr. The remaining information of this file then contains how much density is at a certain point. This is difficult to read, so we need software to look at that and get a nice overview. We can use Vesta, and we ask Vesta to run, and we give it the name of the cube file as argument.